First of all, of course, I would like to thank the organizers, the opportunity they give me for being today here, or speaking today here. Is really a pleasure to be back to in-person conferences. Right? So I am Jorge Casanova, and I work at the University of the Basque Country in the city of Bilbao, in Spain, here, right? And I would like to present a little bit the activities of my theory group. Actually, I think we are one of the few theory groups on in these conferences, right? About, well, the activities of my group regarding nanoscale NMR, right? Well, first of all, where are we? Because, yeah, so we are here in the north of Spain, in the city of Bilbao, more or less, but not pretty far away from Barcelona, right? And I profit to put a couple of pictures that are in Bilbao, that you can see, right? This is a pretty additional place, right? But, well, maybe in this other picture you can see that the city of Bilbao is doing a large investment on science and technology, right? And that's why we are here working, right? There, by the way. Okay, so this is an outline of this talk, right? So first of all, I would like to give you a little bit of context of why we are working here, because in principle we are a theory group. As a theory group, we have the right of jumping, right? Among different platforms, right? And our background is more regarding quantum control for quantum information processing, but we found that several of the techniques we were applying to other platforms, such as ion traps for dealing with quantum information processing, can be also applied here, right? For nanoscale NMR, in particular with nitrogen vacancy centers, right? Then, well, this is a little bit of context of this talk, and then I would like to develop a little bit more regarding dynamical decoupling techniques, right? Essentially, how to appropriately send in principle a bit sophisticated radiation patterns to allow to tame the dynamics and to modulate the dynamics in the way we want. Right? Also, well, I would like to show you that also we have several ingredients, right? Not only the presence of travel frequencies and the tunings that we can essentially put as we want, right? Also the presence of some random phases that provides with further stabilization of the signal we can generate and see, right? And recently we have also started to watch, right, in the signal processing, right? Because, well, let's say, to send radiation and to tame the physics and to modulate the physics is just one part of the story, because we also have to read the signals we observe from the MDs in a proper manner, right? So then we have developed some techniques based on some, well, old stuff, meaning base statistics, but also with neural network, which is more trendy, if you want, right? Then I will show you some applications to some complex systems that we have been developing. All right, so this is one of the slides that I typically use in different talks for introduce the field of nanoscale NMR. Well, for you this is not a novelty, but I think it's good that I use here a few words that will help me to motivate my staff, right? So, as you know, right, nuclear magnetic resonance NMR is a field that has revolutionized fundamental science and applications, because on the one hand has allowed to study, let's say, central interactions that appear in nature between organic and inorganic matter with the electromagnetic radiation, right? While on the other hand, it has also led to different applications, such as, well, we can scan material, we can try to reconstruct the three-dimensional structure of, let's say, in principle complex proteins, right, or complex molecules. And as it is shown in this picture, it could also lead to magnetic resonance imaging. Okay? So MRI, magnetic resonance imaging, is a non-invasive method that enables to obtain internal images of soft tissue, right? And that's why it's a very powerful diagnosis method, which is used nowadays in hospitals worldwide, right? However, and despite all these techniques, these NMR techniques have strong limitations regarding sensitivity, and the reason that underlies this is because, that signal depends on the nuclear spin polarization of the signal we are watching, and typically it's very low at room temperature, right? So the thermal polarization typically is pretty low. So, so in this frame, right? So nanoscale NMR, the field of nanoscale NMR represents a quite radical change of paradigm, because essentially what we are doing is to replace this standard NMR apparatus by a quantum sensor, right? Such as the nitrogen vacancy center, which is presented here in this picture, right? And I mean, the nice idea here is that, well, even the signals emitted by individual, let's say, elements here in a certain molecule could modify the internal degrees of freedom, the internal quantum degrees of freedom on the sensor, and that's something that we can do, right? That's very well, yeah. Actually, I mean, during the development of this conference, I have some funny conversations with some people in the audience, and in some way they are telling me that, okay, in some way we are doing a little bit of the same, right? So, because we send radiation and we can modify everything and see what happens, right? Yeah, fortunately we have a new tool, right, to play that offers different alternatives, right? Then, okay, that's the stuff regarding nanoscale NMR, and it's a field that is essentially promised individual spin detection. Well, not promised because many people have already measured and observed it in the lab, right? Also, high resolution magnetic resonance imaging, if we are able to, let's say, provide or design nice techniques to hyperpolarize fluids or even to produce efficient contrast agents, right? And also, in principle, well, I know many people is trying to look in this direction, right? Not only molecules, also cells or whatever. All right, so this is pretty good, right? But we are also facing different problems, right? Here we have one of them, because essentially we have, from a purely theory point of view, essentially we have one element, right, which operates in this regime. For example, this is DMB, right? One can always create a qubit, right? Or, well, some sensor which is separated by an energy difference of gigahertz, right? And then we want to couple it with another element which essentially operates, lives in a different energy scale. It is a nuclear spin that, depending on the static magnetic field, okay, could be megahertz, right? So essentially these two guys cannot talk, right? They cannot exchange interactions among them because of this energy gap, because there we have a pretty strong energy penalty, right? Then what we can do is to say, okay, let us supply that energy difference from outside, right? By, for example, introducing microwave radiation, okay? So this is the Harman-Hahn typical resonance condition, and actually, to the best of my knowledge, it represents one of the most standard sensing mechanisms used for establishing connection, for essentially for bridge the energy gap between sensor and different targets, right? Okay, so then the people have been working. Oh, sorry, this is like as I told you, we are a theory group, right? So I will put a considerable amount of equations on the slides, right? Then, well, the people have started to develop different techniques for, let's say, for bridging this energy gap between sensor and targets, right? For example, here, right? Well, that's a typically common sequence that the people introduce, this XYA, and it's very common because it has very nice properties regarding robustness, right? So essentially it can cancel different type of errors on the stuff, right? Well, so this is the typical Hamiltonian that describes this simplified system, and here we have, let's say, the driving, right? Which is our, let's say, the tools we are going to use, right? Then, right, well, essentially, if one manipulates properly the equation, in the end, what finds is this other element here, this Hamiltonian, right? Where here we have the Larmor frequency, which is the, let's say, the velocity of the nuclear spins, right? And here we have this modulation function, which is something that appears because of our external drivings, right? So we can drive, and in the end, what happens is that what we are doing is to try to put, let's say, to imprint a tone on the MD, and when this tone, when one of these frequencies essentially matches one of these other frequencies, so what we have is a resonance, and we can detect something, right? Good. Well, so yeah, so the idea is that, well, typically one can consider that this, let's say, the time that we invest for rotating one MB from 0 to 1 or from 1 to 0, right? Essentially to deliver a pipe pulse is something which is instantaneous, right? Typically it's good, well, it's a good approximation. Let's say at this level, instantaneous means that it is fast, very fast compared with other energy scales on the system, right? And typically that's the case, of course, depending on the static magnetic field we are putting into the sample, right? So in principle, right, if that's the case, so we can drive, we can see that, okay, these are the 5 pulses, right? X, Y, this is an X sequence, and the corresponding modulation function of the has this aspect, right? In blue, okay? Fine. Then, of course, as this is a periodic function, it has associated one period, and one period has associated one frequency, right? In particular, for this case of instantaneous pi pulses, so this f set frequency is a step function, right? Then it has a period, actually from here to there. I don't know if you can see the pointer, more or less. Okay. Good. Then, as this is a periodic function, right, we can always write in terms of Fourier series, right? And then, if one of these tones, if one of these harmonic matches one of these frequencies, so essentially the representative Hamiltonian is this one, right? Fine. And for this specific aspect of the function, so this fk has this aspect, we can calculate analytically without many problems, right? That's fine. So this is the method. Of course, well, if we want to go for situations in which, let's say, the nuclear spins start to rotate a little bit faster, or we cannot put enough microwave power into the system because we can, or because we don't want, right? Or we don't want to increase, for example, to put heating on the sample because we don't want to damage, right? So essentially, we cannot consider anymore the pulse, like the pi pulse time, instantaneous, right? So essentially, the pulses has a certain width. Then, what we found is the following thing, right? That in that case, when p pi is different from 0, right? Essentially, well, the idea is more or less the same. So this is the Hamiltonian that describes the physics of the system, right? And then the modulation function is a little bit more funny, right? Like this one. Good. On the other hand, as the pi pulses are something which has take some time, right? We have also observed the appearance of other modulation functions because when the NB, imagine the Bloch sphere is rotating from 1 to -1, it also spends some time, and it also has other components in the xy plane, right? So this typically leads to the presence of these other modulation functions, which means that this Hamiltonian should be a little bit more complicated and contains all the modulation functions, including x and y components on the Bloch sphere on the NB. And this, well, could lead to false identification, right? That's a problem that we could have, right? And we will talk a little bit later about that. But interestingly, I mean, this is not the only effect that happens because essentially the presence of this modulated function, when we introduce these pulses, which has a certain width, right, is this one, and they can follow the same story I told you before, right? One can look for a certain resonance, right, and in the end, it will find this effective Hamiltonian, right? But now this f of k has this aspect, which is, a little bit more complicated, right? But unfortunately, here the scaling is this one, right? It's 1 over k, where k is the harmonic we are using, but it also appears this factor alpha squared, right? And alpha is just the relation between the pi pulse time, right? The time we invest for doing the rotation, and the Larmor period, which is 1 over the frequency of the nucleus, right? So again, in situations when the nucleus is rotating fast, right, because we're introducing a quite large static magnetic field, or in situations where we cannot introduce enough microwave power because we cannot or we don't want, right? So this f of k, which is one element that determines the strength of the interaction, actually has this aspect, right? I mean, here we have this plot for several harmonics, right, for different harmonics, and always work in the same way. So that means that essentially, I mean, we can draw the sample and observe nothing, right? Because the effective interaction goes to 0, right? Effective interaction because this guy, this f of k, that depends on the sequence we're introducing, essentially has this correlation. That's something that we found in this paper. Okay, so, well, to check these ideas, right, so more or less what we want to do is to say, okay, so we have this problem, right, because the Fourier coefficient behaves 1 over k, like in the case of instantaneous pulses, but it also has this additional factor, which is not good, and it's essentially tells us about enough information about how much power we can put in comparison with other energy scales of the system, right? Then we took some numerical simulation, we did some numerical simulation, and of course we observed this behavior, right? So we will consider one NB and certain target, in this case for 2 Teslas, right? And then if one delivers top hat pulses, standard top hat pulses, so one would find this green line, while, right, in the case of delivering top hat pulses, but this time total instantaneous, one can get this other blue, right? So, I mean, this actually is a plot that reflects this problem, the presence of this alpha. Okay, good. So now, I mean, we started to see how we can, let's say, solve this kind of problems, right? And fortunately, we found several alternatives, right? In particular, right, what we can start to do is to try to start introducing more complicated pulse sequences, right? In this case, well, this is a case where we develop one radiation pattern involving continuous drivings, but this time with a modulated amplitude, right? So, and the idea is that, okay, we send some drivings and we are imprinting to these drivings additional tones. And these tones will, in some way, resonate with faster frequencies on the system, right? Well, you have here this Hamiltonian that essentially is describing this system, perhaps a little bit more complicated because we are introducing several nuclei, right? And then here you have HC, which is the control Hamiltonian, which is the Hamiltonian that we will use for establishing appropriate resonances, right? And we selected, okay, we say let us take, for us this Hamiltonian has this aspect. This omega, right, is the frequency, which is resonant with the value of the NB transition, right? So this means that it should be gigahertz approximately, right? And then this amplitude, this Robert frequency, has this aspect, right? So two terms which are static, right? And an additional term that is not directly related with the power we are introducing, but with the way in which we modulate the amplitude, right? Okay, so after some maths, right, one can find that essentially, because of the presence of this phonic driving, the resulting Hamiltonian is this one, right? This element. So these plus and minus are first states of the end, right? Good. Then the idea is that, okay, we have this new element here, this is pretty common, but we have this new element here. And then, fortunately, we have well, different machineries, right? For example, we can use the Jacobi-Hanger expansion, which in our case allows us to write this guy here. I mean, in terms of using Bessel functions, and in the end we can approximate like this now, right? And now it's pretty funny now because this cosine with this nu, which is just the way in which we modulate the controls, appears here, right? And now we can use this nu to establish some kind of resonance with the elements there, right? Of course, there is always a price to pay, and in this case is that, well, yeah, our strength appears modulated by this Bessel function, which is typically proportional to the alpha omega 1 divided by nu, right? But it's a little price to pay, I mean, compared with when we can measure after, right? And we introduced this kind of controls in this paper. Well, and these are some results, right? Of course, numerical simulations, I mean, that we did from the very beginning, right? And we were considering a case in which we have one NB and 3 nuclear spins, and as you can see, right, so we can observe this good behavior, right? So we can really detect the presence of resonances. So we selected 2 different cases, right? And all of them are according to this type of Hamiltonian, right? Now, as you can see here, the resonances occur close to 10 megahertz, right? And then the controls we use for generating this spectra includes Rabi frequencies which are on the order of 1 megahertz. So these are pretty far away from the Harman-Kardon resonance conditions, right? So in principle, they shouldn't provide any kind of information, but because of this appropriate modulation, we can, right? So we have 2 examples, right? Essentially this for this time, and this is a little bit longer because one of the frequencies is smaller, 0.5 megahertz, but this also good because in principle we could provide with more precision in the measurements. Good. Of course, this was just one part of the story, right? Because, well, the previous scheme is good, but it's not especially robust, right? Because as soon as you start to introduce different errors on the system, we can start to see deviations on the obtained spectrum, right? Then we started to see what happens when instead of delivering a continuous radiation pattern, we start to deliver radiation in a kind of stroboscopic manner, mimicking what happens with standard sequences such as HY8 or others, right? Then what we did is to, okay, let us apply some of the techniques we are used to apply in quantum control for quantum information processing, such as inverse engineering or shortcut derivaticity, right? And see what happens. And the idea is the following one. So here, to show you how this works, I prefer to introduce this Hamiltonian, which essentially is here, right? So it's the coupling of the ND with some, let's say, classical signal, if you want, right? And here we have the control. Okay. So now in our control, of course, this Rabi frequency is time dependent because what we will do is to assume that this is delivered stroboscopically, right? Then in this cosine has this omega, which is again on resonance with one of the NB energy transitions. And here we have some detuning. I mean, that is also an ingredient to get introduced, right? And this detuning, this different energy is much more smaller, as you will see, than this frequency, right? Then, after some stuff, right? After working a little bit with the equations, in the end, what we got is that this is the effective Hamiltonian that appears, right? And now, because of this design, so what we have here is some Rabi frequency. I mean, here we have several ingredients. We have this Rabi frequency, we have this detuning, which is related with this one through some integrals, right? But nothing complicated. Essentially, we have all the degrees of freedom here, and here we also have the phases. Okay, so we have 3 degrees of freedom for playing, right? And try to find good mechanism for that. And then the story is a bit the same, right? So the Hamiltonian that determines the interaction between the ND and the classical signal, in this case, is this one, right? And because of the presence of this control, we can induce some modulation function and look for the resonances, right? Okay, so now you can see a little bit here how is the mechanism, right? So in principle, we would love to apply a sequence of pi pulses and imprint some rhythm in the NB such that we get some coupling with our targets, right? So in this plot, I have what I am representing is the presence of this classical signal, which is here oscillating, right? And here, this f of t is the typical aspect of the modulation function. Sometimes it's up after a pi pulse goes to -1, and after a pi pulse, which is represented here, what I want to represent is that it takes some time, right? So again, after a pi pulse, it goes back to 1, right? Then, as always, this f of t, can be rewritten in this manner. We can select an harmonic and try to look for the resonance, right? And again, right? For example, in this case, it is appropriate to use the 11th harmonic, this one, right here. And let's say the value of this harmonic can be calculated, can be computed, right, by solving this integral, right? Then this part is interesting because during this time, right, essentially this fs is essentially 1. And what we can see is that there are many parts that cancel each other, right? So for example, this area is cancelling this area, and this area is cancelling this area in blue, right? So only the last part here in yellow is the one that is really contributing to this integral, thus is the only one that is contributing to the effective interaction, right? And the same story in the middle, right? So as you can see, this part cancels this one, that part cancels that one, that part cancels that one, and in the end it's just this yellow. And the same story at the end, right? What does it mean? That essentially, if this is the pi pulse time, and if we are able to cancel the effect of the rotation of the NB during the pi pulse time, essentially, we could make these pulses much longer, without any problem, right? Because the effective interaction would be the same, because of the harmonic we are choosing, right? Then, this tells us, okay, good, so we can do extended pulses, right? And this is good because this means that in the end what happens is that the microwave power we will need is smaller, right? And then we have a new playground here to essentially to play, right? A new scenario. Okay, so this is represented essentially here, right? So the issue is that, okay, we have some f of t, but as I told you, here we have several cancellations, and then here during this region, we have to design some funny aspect for the pulse such that the contribution during this region to the integral is 0, right? But this story is essentially similar, right? So essentially, if we are able to cancel the contribution of the modulation function during this region, essentially, well, the coupling we will have will be essentially the same, right? Because here we have this guy cancel this one, but essentially you can see this yellow area is the same one that right? Essentially survives. And the good thing here is that, well, essentially we can invest less amount of energy. No? And for that, we have all these ingredients here. Then, what we did is to apply some techniques based on inverse engineering, or in shortcut to adiabaticity, which in some way tell us that so we have some parameters, we put these parameters on the state, and then we want to find out which are the controls, right? For example, right, in this case, right, well, we apply our techniques and we put some ANSA. There are many, this is just one of them. Of course, we can provide with specific designs for each of the problems, right? And we find this funny aspect for the radio frequency, and this is for the retuning, right? And we simulated this situation and we found this result, right? For example, here in blue, right, this blue solid line, you have the results one would find in case of considering a system with one MB and one carbon-13 in Teslas, right? And when we are considering instantaneous pulses, right? Pulses which essentially contain an infinite amount of energy, right? However, here the squares are the results we got when implementing our sequences, our controls, right? Then, as you can see, I mean, the overlap is pretty good, right? However, here the cycles, right, that we got are the results that one would get in case of delivering standard sequences based on top 5 pulses with the maximum energy, right, approximately with 30 megahertz. So as you can see, here this is the, right? This means that we can produce, sorry, 3 minutes. Oh my god, okay, sorry. Well, so this is the result, right? Which means that with extended pulses we can get the results corresponding to the cases with infinite power, right? Good. Well, I think I have to run a little bit, and then the idea is that okay, these techniques based on inverse engineering can be applied for other things. So in particular, we have also been working in how to develop, how to deliver ion guns, right? It's, using ball traps, right, for creating defects with a good amount of lateral resolution, right? So for that, you can check the poster of Angel Provalina, who is sleeping there, right? Good. I think I have to run a little bit, so unfortunately I cannot show you these nice results. In this case, done by Ferro, right? With this nice collaboration with that. But essentially, the presence of these random phases. Here we demonstrated that if we introduce this other degree of freedom, so we can remove the presence of spurious resonances, right? You can see here, right? Here you have some results in orange that essentially here wanted to do some hydrogen, but the presence of this carbon could lead to additional bumps into the signal that obscures the signal emitted by these standard sequences, right? In blue, right? When we introduce random phases, we can see the resonance due to the hydrogen aspect. So these are all different ingredients that we have. Of course, as I told you, right, so the presence of random phases can be, or these sequences can be applied to other systems, in particular for quantum information processing, in this case for Ethereum. I think I'm going to skip because this part is also interesting, right? Well, as I told you, so just to deliver radiation in an appropriate manner, right, is good, but this is just one part of the story, right? Because essentially, we have to be able of reading appropriately the signals emitted by our sensor. This is one case in which we were working with our friends in Jorge, right? And they they do some experiment of sensing classical signals, in this case with an Ethereum-based ion, right? And, well, sometimes the signal is easy, right? But depending on the working regime, the signal emitted by this ion could be a little bit more crazy, right? So, yeah. So we have the theory that describes more or less this stuff. But in this last case, we don't have a linear relation between target parameters and the things we can harvest from the signal, right? Then, the good thing is that by using, for example, neural networks, right, and essentially we produce many signals, we can train a neural networks, and in the end, even in complicated signals like this one, we can get the parameters we have for input average, right? So I am going to end. So I also want to tell you that, well, so we have been working in different systems, in particular working with microsite-based labels, right? For details, in this case, I have no time. Today, Carlos will present the poster about this info, right? And then this is the summary of the talk. And before thanking you for the attention, I would like to present the people here in my group, right? Here you can see a picture of the typical aspect of weather. Bilbao, rainy and windy, some way fine. And thank you for your attention.
How does the longer period survive in presence of realistic T1 and T2?
Yeah, of course. I mean, that's a problem to be included, right? But essentially, yeah. So the longer the period, right, would mean the longer the harmonic, right, the smaller the signal we get. So that's always a problem, right? But here we are comparing that problem, essentially, that it's always there with nothing. In the case you cannot deliver enough power, right? So you cannot deliver enough power, you get essentially nothing, no signal. However, using this kind of techniques, you get something, of course affected by this kind of problems, right?
I have a question. Was better adding one higher harmonic, or like go to a shorter harmonic, or adding more optimal control for the pulses?
More optimal control for the
Yeah, like optimizing the pulses, the strong pulses, or is it better to go to a shorter harmonic?
Yeah, my experience with these things, told me that essentially it's better to start here and then, use this as a seed and then put optimal control on top of this, right? That's my experience. We can discuss about this.